Welcome everybody to mathematics, and you will. So I will towards the end of uh, the talk. I will give you my wishes. So this is at a Aram ceremony. Uh, we gurus, we are hoping that you will study mathematics, and it's an opportunity to tell you to give gyan to you, of course, but that we will do for the next 3 years. But it's also to express our wishes. So on behalf of the department, I will express some wishes. And first of all, the topic is Ramanujan's most beautiful identities. So you have, I'm sure you have heard of Ramanujan. Have you heard of Ramanujan? And you can, I keep track of the chat, so you can type your responses in chat at any time. Okay. So if you have you heard of Ramanujan? Please give me a sign of life on the chat. Okay, thank you, Garvit and Ayushi. Yes, so Ramanujan is one of the very well-known geniuses of India, and he was a mathematical genius and very prolific. And it is now 100 years exactly since he passed away. So this year is the centenary of his passing. So it is appropriate to some extent that your first lecture is on something about Ramanujan. Okay, so uh, the topic is partitions. Okay, so this is going to be a blackboard talk. I'm going to write on a piece of.
Gaurav, can you, hello, Gaurav,
Yes.
can you expand it? That is, uh,
So you can change on your screen, make it
you
big.
can, that side you can, please remember that you can change the screen. Yeah, okay,
Yeah.
okay, Gaurav. Got it. Sorry.
So the topic is partitions, and within this context, I will explain. And unlike in the course where you may not understand 100% of what's going on. So because I may be skipping steps, I may be doing things quickly. So please feel free to stop me. I mean, if necessary, we'll go beyond time. Okay. So what are partitions? So a partition. Okay, also I should mention that it helps to keep a piece of paper and keep writing whatever I'm writing. So somewhere writing and taking notes seems to improve the brain's process for absorbing what is going on. So you can watch it, but then you may forget. So it might be a good idea to keep a pad in front of you. So a partition is a way of uh, writing a number as an unordered unordered sum of natural numbers. So for example, here's an example. 15 I can write as 5 plus 4 plus 2. So that's 9 plus 2, 11 plus 2, 13 plus 1 and 1. And when I say unordered, what I mean is that 4 plus 5 and 5 plus 4, for example, are the same. So I don't say these are separate, So in this order, I usually go from biggest to smallest. That is a partition. And here is a picture to represent it. So what I do is I use boxes. So 5 for this 5, then 4, and then 2, then 2. So this is 5, 4, 2, 2, and then 1, 1. And these boxes are called Young diagrams. And they represent the partition. So this is 5, 4, 2, 2, 1, 1. Okay. And almost immediately we have our first theorem. So if I write a partition like this, I can also, I'm counting the boxes from left to right. I can also count the boxes from top to bottom, right? So I can count the boxes here. That's 6 of them, then 4, then 2, 2, and 1. So the theorem is that the number, so this I'm using to denote number. This is number, short form for number. Number of partitions with k parts. This is equal to number of, so the number of parts is 1, 2, 3, 4, 5 is equal to the number of partitions with largest part k. So this guy. And in fact, one can also do, instead of k parts, we can also do less than equal to k parts and less than equal to k. So equal to k and less than equal to k, it works out. It's the same. Okay, so the proof is easy. Counting from rows, instead of counting from rows, count from columns. So what am I saying? Why is this a proof? I'm saying that for every such diagram, there is another diagram, and there is a one-to-one. It's a one-to-one correspondence. So what does it mean when the number of things are the same? What does it mean? So when you were very small, really small babies, then the math teachers taught you how to count. So they put a picture of one apple and they said, okay, this is one. Then they put 2 oranges and they said this is 2. So what was happening was that the number of objects was being associated with some number. And what we are doing is we could associate number of object, 1 apple with 1 banana, 2 oranges with 2 some other fruits, and so on. So here what we are doing is we are associating each object, each partition with equal to k parts with a partition with largest part k. And I can do the same with less than equal to. And what I do is I simply take what is called the conjugate. Okay, is this clear? So that's your first proof. It's a proof by picture. And the next topic is how to enumerate, how to list. Okay, I should mention that most of what I'm doing is known from Euler and Jacobi's times, but some of it is in my joint work with Hartosh Singh Bal. So this is a joint work, and Hartosh is he's a writer and a journalist, and he was my school friend, and we've been discussing mathematics since we were children. So since we were your age or even before. So it helps to have friends to talk mathematics with, and I hope you find such friends in your class. Okay, so how do you list partitions? Here's a technique. What we do is we represent a part with x with the symbol xk. So I represent a part with xk. So for example, if we have x5 plus x4 plus 2x2 plus 2x1, I'm representing this. This is 5, and this is 4, and this is 2 plus 2, and this is 1 plus 1. So same partition, 5 plus 4 plus 2 plus 2, I represent like this. And what is interesting about this way is that if I add an x1 to it, I get a partition of 16. If I add x2 to it, I get a partition of 17. Right. So just by adding these xi's, I can get a partition. So let me make a partition. So this approach helps me make a table. Okay, so here is n, and let me look. These are the partitions. And this is the number. And this is what we call, this symbol I'm using, this function I'm using to say number of partitions of n. Okay, so 0, we say there's an empty partition. So I will explain why later. So why this is necessary, I'll explain later. For n equal to 1, I have one partition, x1. So this is the same as saying it's 1. And there is 1 over here. For n equal to 2, I have two partitions. One, if I add 1 to it, so 1 plus 1, that's 2x1, and then x2. For x3, I have 3x1, x1 plus x2, x3. Okay. For 4, I'll have, so I add 1 to each partition of 3, I will get a partition of 4. And then I can add x2 to 2 steps before. So I get one partition here, and then each time I add a new one, right? So if I add x3 here, then it's already covered. It's covered. 4x1, x1 plus x2, x1 plus x3. Yeah, this should be x3. So let's do one more. I hope you've got what I'm doing. I'm adding x1 to this, so it's 5x1, then 3x1 plus x2, then 2x1 plus x3. Okay, then x1 plus 2x2, x1 plus x4. So these are from adding x1 to this. Then I add x2 here, and I don't need to add to this guy because this is already covered. So I add to this chap. So I add only when I need to, when I get a bigger number. So x2 plus x3, and then finally x5. So this new symbol represents this. So just to say, this I have got from x2 plus x3 from this guy, and this one I have got from adding x1 to 2x2 for this one, right? So that's how I do it, and let me write the numbers. So 2, 3, then there are 5, and 1, 2, 3, 4, 5, 6, 7. Okay, so notice, what do you notice first, that if f k of lambda is the number of k's in the partition lambda, right? Then if I if in this partition number of ones is 0, number of twos is 1, and number of threes is 1. So then this is true, that k times fk lambda, and if I sum it, this is equal to n. So this is the definition of partition in some sense. So you can so this is k equal to 1 to n. So you can just read off over here. So 3 times 1 plus 2. 3 times 1 plus 2, that should be 5. And similarly, 1 plus 3 should be 4, and so on. All right. So I hope it's okay so far. All well? Okay. So any mathematics concept, and this is a very big claim, and it was a challenge for both you and your teachers. Anything in mathematics can be thought of as a picture. It can be looked at as some symbols and in some numbers. And then we have this kind of symbolic idea called generating function, which is special which is a special idea. And this idea goes back to Euler. So Euler, I mean, this is pronounced Euler. Uh, how do you think this is pronounced? Well, this is not Euclid, it's Euclid. So this is a German EU. Euler was a Swiss mathematician, and it's pronounced Euler. It's not pronounced Euler. That's the first thing one should learn when one gets into college, if your high school hasn't taught you this. Okay, so what Euler did, Euler considered this function. So is a q 1 minus q squared, 1 minus q cubed, 1 minus q to the 4. So there's an infinite product here, and he considered that. And then if you recall that 1 over 1 minus q can be written as 1 plus q squared plus q cubed, and so on. And this is for q less than 1 and bigger than minus 1. But we will just ignore such things, and we'll say it's equal to this as a symbolic idea. And if you do that, if you apply this idea to all of them, you can write it as 1 plus q squared plus q cubed, and so on. 1 plus q squared plus q raised power 4 plus q raised power 6, and so on. And so on. So there are infinite set of products. Each product is an infinite sum. And let's take a particular element here. So the particular element here is taking a finite number of these guys and take any one monomial from here, one from here, one from here, and so on. Only a finite number of them, because we can't multiply an infinite number as such, but take a finite number and then just collect the power. So first of all, notice that if you just multiply only the ones, then you will get a 1. Then you'll get terms. How do you get q here? You'll multiply this q with all ones. Otherwise, you won't get a q. So you just get 1. How will you get q squared? So to get q squared, you can multiply this q squared with all ones. So you will get 1 from here, and you can multiply this q squared with all ones. So you get another one here, and so on. So here you'll get 2 right here. Do you want me to do one more? Let's do q cubed. So q cubed can be got from here. Then you can multiply this q squared with this q, and you can get 1 q cubed from here. So you'll get, so I'll get q raised power 3 plus q raised power from here 1 plus 2 plus q raised power 3. So what am I getting? I'm getting the partitions of q. So a general term is of this form. You take k1 from the first product, 2 times k2 from the second product, 3 times k3 from the third product, and so on. And this is a sum over all ki's, a finite number of them. And if you collect powers of n, you will get the number over here of ki's such that summation I ki equal to n. So you can collect that, and you go from 0 to infinity. And this is nothing but the partitions. Okay, so this comes from this guy. This fk is the same as this k or k whatever. So I should have put fk here, f2 here, f2 and f3 here. So same. Okay, so this is this is called the generating function. So this is called the generating function of partitions, and Euler noticed that this infinite product uh, gives you the generating function for string. So Euler was when, I mean, 1700 sometime, so long back. Okay, so is that clear? Is that okay? Somebody give a sign of life. When I say is that okay, please write something, yes, fine, no, whatever, in chat. Okay, so Neha, thank you, Neha. Okay, thank you, Rajneesh. Yeah, so you can very easily write other generating functions. Okay, and for example, what about generating function of partitions which have only odd parts? That means they only made up of these parts. So 1 plus 3, 1 plus 5, 3 plus 3, this is allowed, right? And this is very easy because all you need to do is you don't need to take this guy. You don't need to take so all you need is 1 plus q. So this is q square plus so on. This is from 1. And for q square, q raised to 4, you delete that. You don't need this. But you take the one with 1 plus q cube plus q raised to 6 plus so on and so on. And basically what you're doing is 1 over 1 minus q, 1 minus q cube, 1 minus q raised to 5 and so on. So this is a generating function with only odd parts. And similarly, what is the generating function for of partitions with only distinct parts? Distinct parts means that something like this is not allowed. This is not okay. This is okay. So in the parts of a partition, you can't have repetitions. And well, repetitions in this product are counted by, you see, this is 2 times 1, this is 2 times 2, this is 3 times 2. So I don't have these terms. So all I need is 1 plus q, 1 plus q square, 1 plus q cube, and so on. So when I pick one item from here, they'll always be distinct and rest will be ones. That's the idea. So you can do a lot of things, and let me show you the next theorem then. So which is a little bit deeper. So already, what I intend to do is to show you more and more complicated formulas until we reach a formula which is Ramanujan's complicated formula. So each step of the complicated formula you should somehow get that what is the picture behind it. Maybe you don't get 100%, but you get something. So let's see what this is a theorem due to Jacobi and possibly Euler. And I mean, other people have said it's Euler, but recently I heard a talk where the author, who's an expert on partition, said that he couldn't find it in Euler, but he found it in Jacobi's work. So what he's saying is, what you do is, so this is a pictorial way of arguing with these formulas, and I had written in my abstract that this theory allows very complicated formulas to look very trivial. So this you have to understand very well. Okay. So what I do is I take a square. So suppose this is a square. So of side k. Okay. I take a square, and it is generated by this quantity. Okay. And what I do is I attach a partition with less than equal to k parts. Now, what is the generating function of less than equal to k parts? Okay. Well, let me attach another one first, then I will. So here I attach another partition. Okay. And this is a partition with so this is less than equal to k parts, but this, the largest part is less than equal to k. So I get a partition of n which has this square in the middle with a partition attached here and partition. So what is the generating function of this guy? Partition with largest part k. Well, I just don't want anything beyond k, right? And we just had a theorem which said this number of partitions with less than equal to k parts was equal to the number of partitions with largest part. So this is also the generating function for this. So generating function for both these guys, is this. And generating function for q to the for k square is just k square, so it's equal to 1. If this is so what do we have? So the generating function for these kind of partitions is 1 minus q, 1 minus q square, 1 minus q cubed, and so on up till 1 minus, 1 minus q to the k for this guy, and there are two of these. So what am I saying? I'm saying that if I expand all this guy in powers of q, suppose I write them as something q raised per k, q raised per n, then this n is made up of k square plus something smaller than some partition smaller than some partition smaller of this kind and some partition of this kind, right? If I expand this guy over here, and suppose I take all k going from 0 to infinity, then what do I get? I get some partition of n. So if I take, so every partition has some square like this, the biggest square, and it can be decomposed into these three parts. So if we do this and we expand it, I will get all partitions in this case. So for this guy, I'll get all partitions. And what does that mean? That means that this has to be equal to this guy. Well, this is a term, but it keeps going on. Okay, so does that make sense? Or is it too much above the top? So what I'm saying is that if I expand this, let me write another color. So let me say, well, this is, let me write this. So if I expand in powers of n, q raised per n, the coefficient will be number of partitions. And each partition, here the same thing, because each of these individual terms, they have every partition has some square and then something smaller here, something smaller here. And then I sum. So this is for some k, and then I sum over all k, and I should get both these things the same. And if you got this far, then you really understood Euler, how he used to think. Okay, and let's do another one like this. What I do is, instead of attaching a square, I attach this one, second, also by Jacobi or Euler. I attach this guy. So 1, 2, 3 up till k, and this is up till k will give me q raised per k plus 1 over 2, right? This is the formula for the sum of the first n. And then here, in this place, I attach a partition with less than equal to k parts. So for this guy, the generating function is 1 minus q square up to 1 minus q raised per k. Let me write it like. So this guy is made up of a staircase like this, 1 plus 2 up till k, and a partition with less than k parts, and the net result is it's a partition with distinct parts. So if I sum all this guy over all k's, which is the same thing as this, I should get the generating function of distinct partitions. So I should get this. So again, an infinite sum is equal to an infinite product, and by which we mean that um, um, if I take any coefficient of q, so take the coefficient of q raised per n, this will give me the number of partitions with distinct parts. And same thing here. If I expand each term if I write it as q raised per n something, these two guys are the same. And these two guys have a meaning aside from convergence. You don't even have to worry about convergence in this. So these two guys are equal, is a combinatorial kind of theorem, which follows for formal power series. So in your algebra course at some point, you will see formal power series, and when you see it, let me write it down, formal power series. When you see it, then you tell your sir or ma'am that we know what they are, Okay, so that's wonderful. Now let me do one more theorem of Euler. And this will tell you how Euler used to think, and your analysis professor is going to really have to explain why this is okay. Number of So, there are a lot of things which we don't know that about what all courses are going to come. So when I mention the names of courses, it means that these things will be covered at that time. So when you come to that, I mean, I don't know when they will come, maybe in first year, maybe in second year, you'll know that why are those courses necessary. The courses are necessary because Euler and other people have done all this math, and we have to explain or understand that. So Euler said that the number of partition with distinct parts is equal to the number of partitions with odd parts. And I'll give you a proof. So the generating function of odd partitions we saw was 1 minus q, 1 minus q cubed, 1 minus q raised per 5, and so on. And some terms are missing, so let me insert those terms. So I'll put 1 minus q, and then 1 minus q square is missing, so let me put 1 minus q square. Then 1 minus q to the 4 is missing, so I'll put 1 minus q to the 4. Let me put 1 minus q raised per 6, and so on. Is that okay? So again, it's it works, and then I can cancel. So if I cancel this, what do I get? I get 1 plus q. If I cancel this guy, I get 1 plus q squared. If I cancel this guy, I get 1 plus q cubed, and so on. So this is the generating function of distinct partitions. And now your analysis professor will really complain and say that how can you cancel an infinite number of uh, times? Euler could do that, and yeah. So is this allowed? And the answer is yes. And one can you'll probably see it in an analysis or complex analysis course. And if you don't, you can call me at that time, and I will explain it to you again. So Euler did a lot of multiplications and infinite this that manipulations, which later on mathematicians that were forced to try and prove. In this case, there's not much difficulty because it works in a formal power series, and I will actually show you on a computer towards the end how this works. I mean, how these. Okay. All right, so far. So this was Euler. Now, are you ready for Ramanujan? So, so the identities which we are going to talk about are called Rogers-Ramanujan identities, and I will briefly go over their history later. But this is what they are called. So Rogers was an English mathematician, and he discovered them about 20 years before Ramanujan. But nobody knew about it. So, but I will talk about that anyway. So the starting point for this is that distinct partitions, distinct partitions, uh, the difference between parts, you can think of it as saying that the difference between parts is at least one, right? So when we have a distinct partition, remember this was the smallest distinct partition, and we attached something here. So this had difference between parts was exactly one, at least one, because we've attached something over here, right? So what about the question that one could ask is, and this is not how Ramanujan probably thought, but this is due to this was suggested by Andrews that so suggested this idea. He says, what about uh, if the difference between parts is bigger than equal to 2. So Andrews suggested that Ramanujan could have thought this way or whatever, or at least he suggested that others may have thought this way. And it's possible that Schur is a mathematician, is a German mathematician who discovered these identities at the same time. He might have thought this way. And he said, what about difference of parts bigger than equal to 2? So remember how we made the partitions for parts, distinct parts. We added, we attached this thing something to here. So what I'll do is I'll make a partition with parts more than 2, more than exactly difference equal to 2, right? So I have this kind of partition. So I have 1, then 3, then 5, and so on. And let's say it's 2k minus 1. So k parts. So k equal to 1, I have 1. K equal to 2, I have 3, and so on. So kth part. And then here I attach a partition. With less than equal to k parts. And here I have 1 plus 3 plus whatever. So how many do I have? So I have q raised power 1 plus 3 plus 5, so on up till 2k minus 1. So I have q raised power. How much is 1 plus 3 plus so on? It's k squared, right? And this guy over here has generating functions. So we are looking at generating functions. This one has generating functions. This, as we've seen 3 times, right? So if you take all the partitions like this with with minimal difference 2, then you will get this as the generating function. And if you take all of them, take the sum, okay, so you can consider this sum, right? So this is the generating function of all partitions of n with difference between parts bigger than equal to 2. So I would say, I'll put it like this, P n difference of parts bigger than equal to 2 q raised. Is that okay? Is that clear? Okay, please give me a sign of life again. Okay, Kirti. Kirti is first off the block. Bhavika, thank you. Okay, Neha, thank you, thank you. So okay, so now this is the sum side of a thing, and you look at the previous theorem. It said number of partitions with distinct parts equal to number of partitions with odd parts. So the question is there some something I can say about the other side? So the distinct parts, this portion generalizes. Can I say some other thing, and can I find something else? So here, I think your professor mentioned something about mathematics not really being computational, and that is where I totally disagree with him. Mathematics of Ramanujan was totally computational. He was a genius where it came to manipulating and adding and subtracting and multiplying and so on. And that's how he got so much stuff done. And so was Euler, and so was Jacobi, all the three people who have I mentioned so far. And so indeed is Andrews, the fourth person I mentioned. And sure, and now you have computers. So I will show you a computer package very soon, which can do all these computations. But anyway, what we have understood is that there is this generating function, which is 1 plus q to the k square. So I'll just write the first term. So k equal to 1. So q over 1 minus q plus q4, 1 minus q square plus q raised to 9, 1 minus q square. And now I'm going to tell you a trick which Euler did. So recall, how do you prove this kind of thing? So let's take this right hand side to be s. And if I multiply s by 1 minus q, then I'm multiplying every term here by 1 minus q. So I get 1 minus q plus q times 1 minus q plus q square times 1 minus q plus q cube times 1 minus q plus so on. And then I have 1 minus q plus q here minus q square here plus q square here minus q cubed here plus q cubed here and so on. And you can see that alternate terms cancel and the answer will be 1. So that means that s is equal to 1 over 1 minus q. So this is called telescoping. And we saw an example in the proof of. So this was also a similar idea, right? There was a telescoping idea. Right? So what's happening is that if I have 1 plus q here, and if I multiply by 1 minus q, at least this q cancels. This is the moral of the story. So this is Euler's trick. So we have this generating function. Let's call it s. So let s be equal to 1 plus q over 1 minus q plus q square over 1 minus q times 1 minus, sorry, q raised to 4 plus q raised to 9. So whatever this infinite series plus so on. And can you tell me what is the leading power of q? So if I expand 1 over 1 minus q here, it will be 1 plus q square and so on. So it is 1 plus q plus some q raised per higher powers of q. This much is clear. So I multiply by 1 minus q, And when I do that, I get 1 minus q plus q times 1 minus q over 1 minus q, which cancels here, plus q raised power 4 over 1 minus q squared, plus q raised power 9 over 1 minus q squared, 1 minus q cubed, so on, plus so on. So when you see 3 dots, it should be 3 dots actually, it means and so on. Okay, what do I get? I get 1 minus q plus q. So I get 1 minus q raised power 4, 1 minus q squared plus q raised power 9 over 1 minus q squared, blah, blah, blah. All right. Okay, now this is 1 plus q raised power 4 plus something. So what do? I multiply by 1 minus q raised power 4 on both sides, and I'll get 1 minus q raised power 4 plus q raised power 4 over 1 minus q square, 1 minus q square plus. So I'm multiplying, I mean, even terms which I haven't written down, I have to multiply there. And what do I get? I get 1 minus q raised power 4. 1 minus q raised power 4 has to be multiplied. So I'll get plus q raised power 4, 1 plus q raised power square, 1 plus q raised power 2 plus whatever. So what do I get? I get 1 minus q raised power 4 plus q raised power 4 plus q raised power 6 plus so on. So this cancels and I get this. So what is the next term I will multiply by? What do you think is the next term? It's 1 plus q raised power 6 plus something. So I will multiply by 1 minus q raised power 6. All right so far? Okay, yeah, Kirti got it. Fantastic. Okay, now I'll show you my computer. So I'm going to stop sharing this and start sharing something else. Okay, so now I'm going to directly contradict Sanjay sir and I'll just share my screen. Yeah. Okay, see my, here you go. Can you see my screen? Can you see my computer screen? Okay, now this is a computer program that I use. It's called Sage. Sage Mathematics. So this is a symbol. So I will just type sagemath.org. So you can go to this site sagemath.org and you can download it and install it, and it is a free open source mathematics software system. So it's a free system for doing mathematics. Everything that you've done in high school pretty much it can do, and I hope you will. I mean, this coming to the wishes, which I will tell later, but I hope you will use it in your learning when you're doing math. Okay, so what I'm saying here is nothing much. This QR fact is a definition of what you can't see is that I'm entering, I'm pressing Shift Enter. So QR fact 3, for example, is this product.
Sorry, sir, your screen is not visible.
It is not visible actually. Gaurav, screen, your computer screen is not. You're doing in computer?
Sir, you have only shared Chrome screen, not the entire screen. So Sage is not visible.
You can't see Sage?
No,
sir, only the Chrome screen.
Okay, all right. Let me share it again. Sorry. Okay, now can you see a screen?
Yes, now it is visible.
Okay.
Yes.
Can you see this?
Yes, of course.
So Sage, it's a sagemath.org. So if you go to this site, www.sagemath.org, you will see this site, and then you can download it and use it on your own. It's available for free, and I hope you'll be able to use it. Now this is my Sage. When you start it, you get this. So here in QRFAC n, I have simply implemented the idea 1 minus q, 1 minus q square, 1 minus q cubed, and so on. This big O simply tells that stop after when you reach q raised per 100. Okay, so if I multiply it out, this is what I get. And this RR1 is Rogers Ramanujan 1. It's a sum of q raised per k square over QR fact k for k in 0 to 20. Okay. And when I do that and I expand it in powers of q, this is what I get in output 20. And what I've done is I have multiplied it. So let me multiply it in front of you. So when I multiply by 1 minus q, I get 1 plus q raised per 4 plus q raised per 6. Then if I multiply by 1 minus, this is what we already did by hand. It's important to do something in hand. So I get 1 plus q raised per 6. Now again I multiply by 1 minus q raised per 6 as Kirti told me to. And I've got 1 plus q raised per 9. Now next one, what will I multiply by? 1 minus q raised to the power 9, 11. Okay, one more I'll do. Now tell me, you don't have to be as smart as Ramanujan to tell me. What's the pattern? So it's 1 minus q raised per 1, 4, 6, 9, 11, 14. What's the pattern? These are 1 or 4. When you divide by 5, either you get 1 or 4. Can you see my pad now? Okay, so these numbers, when I multiply, I'll get 1 minus q, 1 minus q raised per 4, 1 minus q raised per 6, and the next one was q raised per 9, 1 minus q raised by 11, 14, and so on, times s is equal to, and we hope that in the right hand side I cancel everything and I get 1. So I hope, or I conjecture, that I get, so let me write it in another way. Let me organize it in another way. So this is not very difficult for a Ramanujan to conjecture now, that this sum is equal to this product. And on this side, we have partitions with parts congruent to 1 or 4 mod 5. What this means is that, what does this mean? This means that if you divide by 5, you get remainder 1 or 4. So this side is partitions with parts congruent to 1 or mod 4, 1 or 4 mod 5. This side is partitions with minimum difference 2. And that is called the Rogers-Ramanujan identity 1. And there is another one which he had. Okay, I have 5 more minutes, so I can share that with you. So Rogers-Ramanujan 2 is, he takes 2 plus 4 plus so on up till 2k. So he takes q raised per 2 plus 4 plus 2k, which is the same as q raised per k square plus k. And he attaches a partition with less than equal to k parts. So he attaches 1 minus q, 1 minus q square, 1 minus q raised per k. And we take the sum of all these guys and we do the same thing. And we do the same thing, and this time we get 1 minus q squared, 1 minus q raised to 7, 1 minus q raised to the power 12, and so on, multiplied by 1 minus q cubed, 1 minus q raised to 8, 1 minus q raised to 13, and so on. So this is parts congruent to 2 or 3, sorry, there is 3 lines, mod 5. And this is called Rogers-Ramanujan, the second identity. Now, I should add that this technique is of factoring an infinite series. This part is not rigorous. Okay, so this is not a proof. This is not a proof. This is a discovery approach. So this is a discovery approach, not a proof. Okay, but this is a technique of Euler. So there is a computer algorithm called Euler's algorithm, which if you plug in with exactly this idea, if you plug it in, you will get this. So let me before finishing, let me just briefly outline the history. So history is that in 1913, Ramanujan wrote a letter to Hardy. He sent a letter to Hardy in which he included these things. And then Hardy really liked them and he couldn't prove them, and nobody could prove them. And then eventually McMahon, he was a sort of mathematician there who he was a he was Major McMahon, so he was in the army, British Army, posted in India in fact at some point, and then he went back. He published a book in which he published them as conjectures, as partition conjectures, and then Rogers wrote to him complaining that these were his theorems, and at the same time Ramanujan found them in the library. So this they found that Rogers had a paper in 1894, so more than 20, long time before this, that he had already published them. And then they both published more proofs, and they Rogers and Ramanujan published more proofs, and they more proofs followed. Okay, so this is a history. That's why they call Rogers Ramanujan. And here is my wish for you before I end, last minute of the talk. So there is a famous quote which says, "Beauty in mathematics is seeing the truth without effort." So this is a quote by George Polya. Now, what he's saying is that after a lot of effort, after you make a lot of effort, you may be able to see the beauty of the mathematics, and you may have to make the effort. So this is my wish for you for the next 3 years, that I hope may you make enough efforts to see the truth without effort in all that you study. So even on the first day, before going anywhere, you should know that there is everything in mathematics is beautiful. If you make enough effort, you will find it. You will find the beauty for yourself. And your teachers may struggle to explain it to you, but you can struggle to understand it just better. Okay, thank you very much. Any questions? Nobody has asked any questions in the middle, so please ask now. So you can ask me anything. I mean, it need not be relevant to this talk. If you have any doubts about, starting off doing maths honors, then please feel free to ask me about anything.
Anybody would like to ask any question
Yeah,
regarding?
Harsh Gautam is here. Harsh Gautam wants to ask something. He raised his hand actually. Harsh Gautam. Yes, Harsh, you want to ask anything? You can ask. Yes. Unmute your speaker and ask. Yes, Harsh, unmute your speaker and ask.
Hello.
Yes, yes. We are
Hello,
you.
sir. Am I audible?
Yeah.
Good
Yeah.
afternoon, sir.
Good afternoon, Harsh.
Sir, my question is just in mathematics honors, the course which we have opted. Uh, how are we supposed to approach the course and do make the best out of it?
Well, so my advice is that uh, you know, so your professors will obviously guide you through the courses. So there is a curriculum, but nobody stops you from going beyond the curriculum or looking around or finding a book which you like. So going to the library or hunting around for a nice book and reading it and actively understanding it. And all the courses, I mean, almost everything, there are some nice books and something which which will please you. And the idea is to understand enough to know where the thing is coming from. So it's not, so the faculty members will show you, okay, this is how you do it, this is a proof, this is what, but you may not, it may not be native to you. It's not, because it's very different. It's a quantum leap from high school mathematics, actually, this way of thinking. So one thing you have to be convinced about, that your brain is improving a lot by thinking hard, and the other is that only when you think hard it becomes easy. So my one of my professors used to say mathematics is very hard until you understand it. So whatever you understand, it's very easy. So you have to get to a stage where you understand, think about it hard enough to understand the concept and make it easy for you, and easy and beautiful. And once that happens, then you have understood it. Then again, you will find the next thing which is hard. So two pieces of advice: look around for books which you like to read along with the course, and the other advice is focus on the problems. Mathematics is learned by doing mathematics. So if you do something, and the way to do it is to do the problems. So you do the problems, you think about them, do them on your own, discuss with friends. It's a very collaborative activity. Make friends whom you can discuss math with, and it will help you in some sense.
Thank you. Thank you so much, sir. Thank
Okay.
Another one is Mahima. Mahima? Mahima, are you there? Can you listen? Mahima, you raised hand. I think no.
Mahima, unmute your speaker, then you can speak.
Okay, feel free to ask questions, any questions which are in your mind, because you're beginning a very nice new phase of your life. So any queries you have, please feel free.
Sir, please suggest some references.
References for this material.
Yes, yes.
So there is a book by Erickson and Andrews called Integer Partitions.
Please write it in the chat box so that all of us can note it down.
Sure. Okay, so Andrews and Erickson. It's called Introduction to Integer Partitions. So some parts are these symbols x1 x2 is things which I uh, use, and there is a article. If you go to my site, uh, there is a there is an article in Resonance on how to discover the Rogers Ramanujan identities. So some parts of this, whatever we have discussed, are covered there, but it's a mixture sort of from.
Thank you, sir.
Okay.
Here.
Do we have any other question? Anybody else? So Mayank has asked.
Sir, is it true that the what he's asking?
Is it true that the difficulty of math will increase with increment in our year? Yeah, I think that is true. I mean, first of all, the first year will be a quantum leap. Okay, I mean, it's always a quantum leap, and the main reason why it's a quantum leap is the emphasis on the proofs. Once you deal with that, and math, let me tell you that even today, whenever I see something new which I don't know, I find it a little bit tough, and I have to deal with that toughness. And after a while, I'm okay with it. I'm okay with the fact that there will be some parts of math which will be very tough for me to understand. So, but one has to learn how to deal with the emotions of this thing. So, you are fighting with a if you are climbing a mountain or you're running a marathon, it's very tough. But once you are able to do it, it gives you great pleasure. So you have to approach it with this attitude that I can do it. I have to give sufficient effort and take the help of friends. So this is very, very important that you don't feel shy. Ask people. I find it easier to understand from my friends than to read sometimes, and other times I hunt for books to do. But it's don't give up, because the benefits are tremendous. I mean, your brain will. I mean, I tell you, after a while, mathematics graduates just can outthink anybody. The amount of the capability that you will build up if you are able to think is going to be tremendous. And I can. I don't know if so. Well, I hope I've answered your question. Any other questions?
I think right now they are in a situation that they really don't know what to ask and what they are going to have in their future coursework as in the part of in BSc honors mathematics.
Okay, okay. Yeah. So anyway, my best wishes to all the students and the faculty members. And as I said, one of my favorite quotes, which I always keep in mind whenever I'm facing difficulty, is uh, beauty in mathematics is seeing the truth without effort. And the you have to work very hard sometimes to see that beauty, but you will see it. And that is what you should be chasing. You should be chasing that. Don't worry about the difficulties. Do make friends, do discuss with friends. It's things come easier and easier as you deal with them. It's like learning a language. Okay, so all the best to all the students, and it's a fantastic journey you are going for.
So
And
for vote of thank for appreciation of the speakers, please. I think I request you to clap. I hope that you have enjoyed the lecture. Hello, everybody. Yes. Many things. In a short notice, you prepared the things, and this will not be the only. This will not be the first or the last lecture of yours. And you will, I hope that you will be visiting our college till COVID virtually and
Sure.
after COVID, in physical sense. And we will be very happy to see you there in our college.
So
So,
Mahima had a question. I
yeah,
just
yeah.
want, sorry, I mean, it came late, but Mahima, don't worry. Everybody faces the same issues as
Okay.
you might be facing. All of us, including your professors, however good students they are, there's always something. But what you need to do is develop an internal sensor when you have understood enough. That's what I would do. So don't worry, just keep working. Marks are ultimately not a measure of anything except for but your own understanding you will be able to tell. Okay, so I wish you the best.
Thanks, Gaurav. Thanks a
Thank
lot.
thank
Another one is Fahima. Fahima, another student has raised hand. Is
Fine.
Fahima.
Yeah, yeah, they can ask. It is their day.
yeah, sure. I mean, no problem.
Fahima is there.
Fahima. Yes,
No, sorry,
Fahima, you can ask.
Fahami. Sorry, Fahami.
Yes, ask, please. Unmute your speaker and ask. Yeah, then if she
Or
is
you
taking
can,
time, yes, yes.
or you can write in your chat box if you are not.
Kajal Sehrawat. Kajal, you can also ask. Unmute your speaker, please. Kajal Shehrawat, unmute your speaker, then ask the question. Fahmi Ansari, I do not know what they are not. I think some trouble is there.
Okay, maybe you can stop recording now.
I stop the recording, then we can ask the question.
Yeah.
Right now.